Hi friends, here we are in chapter 2. We're looking at section 2.6 and we're going to talk today about algebraic proofs. So here is our vocabulary for the day. We have algebraic proof, and what that's going to be, it's going to be basically an algebraic proof is a proof of an algebra problem, right? Based on algebraic statements. So what's going to happen is it'll look something like this. Let's say you had this problem and you needed to solve it, right? When we solve algebraic problems, you know how we do it. We take some things, move it from one side to another until we whittle it down and we get our x value isolated. And then what we end up doing is taking that x value and saying that we solved it, right? So when you do an algebraic proof, it's going to be in the form of what we'll talk about as a two-column proof, where you have kind of like statements, and then you have the reason why you can do the thing to the problem. So let's talk about this. If you would solve this, you might suggest that we add 5x to both sides so that the 5x is on either side, right? So that we get all the x terms on one side, which would be totally legit. What a proof asks you to do is tell why you can do this step. And the reason why we can do this step has to do with some properties of equality. This is honestly the addition property of equality. And you'd write that there, right? You write the addition property of equality. Let's do that, prop of equality. I'm making this really look bad. And then the next step, you might have something like, okay, well, 2 is equal to 12x minus 22. After you get that, the next thing you might want to do to solve this problem is to add 22 to both sides. Again, this is the addition property of equality. You'd write that as the reasoning. Once you've done that, you end up with 24 is equal to 12x, and then you would write, well, what's the next step? You're going to divide both sides by 12. And why can you divide both sides by 12? It's called the division property of equality. We're going to get to those properties soon. So an algebraic proof is when you actually do the algebraic step, but every step you're going to justify each of the steps as you go along. I hope that makes sense. So you can write this down for a definition. You could write a proof made up of algebraic statements that are justified by properties, and the key to a proof is that you have justification. And so two-column proof is a style of writing proofs. It's different from our paragraph proof in that it's written as a true listing of a statement and a reason, okay? And your reasons, so your statement will be anything that you want to say leading up to an idea. So your statements will have, and it's going to depend on what we're trying to prove, your statements are going to be a list of things that you want to say about the thing you're proving, and your reasons will be made up of postulates, right? Remember we talked about postulates or axioms. You're going to have some theorems in there. You can have properties like we're going to discuss today, and you could also have some definitions in there as well. So that's going to be the reasons for all of the statements that you're going to make and leading to a particular conclusion. So you'll lead to a particular conclusion. So a two-column proof, another name for a two-column proof is going to be a formal proof. So a two-column proof is a proof that's written up with statements in one section and reasons on the other side. And so with that, let's get to a couple of examples. As I'm glancing at this first example, I see that we actually probably should work on our properties first. And I know this is going to be a little bit boring, but I want you to stay with me because many of these you already know. So let's take a look, and we won't spend an eternity on it, but we will spend some time. So the addition property of equality. I'm going to expect that you know these. I'm going to expect that you have these properties memorized. But what I do want to say is that you have most of them memorized already. So the addition property of equality is basically saying if you have two things that are equal, like A is equal to B, then if you add the same thing on both sides of that equation, it's going to stay equal. You know this. This is how you solve algebra problems all the time. So when you are adding stuff to both sides of the equation, let me make this bigger. When you are adding stuff to both sides of the equation, right? When you're adding stuff to both sides of the equation, it stays equal. Your equation stays equal. If A is equal to B and I add the same thing to both sides, in this case C, it's equal. All right, good. Subtraction property of equality works exactly the same way. I start off with two things that are equivalent. I subtract the same equivalent value from both sides. Guess what? Those two things are still equivalent. I told you you knew this. See, look at you. You didn't believe me. You're like, this is too much to memorize. But now you're realizing how easy it is. Look at this. If A is equal to B, then A times C is equal to B times C. This is a lot like these guys. If you start off with two things that are equivalent and you multiply both of those things by the same value, you're still going to maintain equivalence, right? So if A is equal to B, then A times C is equal to B times C. Over here, this one might throw you for a loop for a hot second, but let's see if we can break it down. The division property of equality basically says, again, starting off with A is equal to B, you'll notice that they tell us that C does not equal to 0. Well, why on earth would they tell us that? They didn't have any extra little caveats about C up in here. Well, the thing is with division, if you haven't picked it out already, is you can't divide by 0. So they almost had to put this in here like a disclaimer. By the way, C does not equal to 0. So as long as C doesn't equal to 0, this rule is going to hold just like the others. The division property of equality tells us if I start off with two things that are equivalent, A and B, and then I divide both sides by some number C, knowing that C is not 0, then that equality is maintained. I told you you knew it. I told you. All right. So these four you know. You've used them all the time, even if you didn't call them by that name. I'm going to jump down to the bottom because these two here you know very well as well. So this isn't going to take much effort for you to memorize because you already got them. Substitution property of equality. This one says if A is equal to B, then A can be replaced by B in any equation or expression. Let's do that again. If A is equal to B, you got these two values that are equal, then the value A can be replaced by B anywhere in an equation or an expression. You've known this before, right? You've seen this. You've seen this back in the day when your teacher would say, A squared times B minus C, let A equal 4 and B equal 2 and C equal -3. And you'd have to plug all that in and do the problem. You know what that was? Substitution. You know what substitution property of equality says? You can substitute if you got something to equally substitute it for. And so yes, here's another one that you already know. And this one down at the bottom is just cute fun. Everybody likes it. It's the distributive property. I think it is the most recognizable algebraic property in the world. The distributive property. And so the distributive property says, hey, if I have A times the quantity of some B plus C, that is the same as saying A times B plus A times C. And this is one that we've accepted and loved for a long time. So now that we've gone over all the stuff that we already know, right? I've highlighted all the things that we know. The last couple of things that we need to talk to are these little three things in here. And you may have seen them. You may very well have seen them. But since they're sort of new, I'm going to highlight them in red and talk about them. So we've got the reflexive property of equality. This is a very obvious kind of a principle, but it is necessary when we consider the idea of justifying our actions in mathematics. So for us, I like to look at the reflexive property of equality as the reflective property of equality. Get it? Not yet? I'll show you. You get my drawing here? It's me looking in the mirror. Who do I see when I look in the mirror but myself? My reflection. Therefore, the reflexive property of equality is like a reflection where the same things on either side of the equal sign. This was brilliant in my head until I draw the picture, so I'm going to get rid of that and continue on. But reflexive property is basically A is equal to A. Anything is equal to itself. Sorry about the picture. Okay, so moving on, let us talk about the symmetry property of equality. So symmetry basically is telling us if A is equal to B, then we can say that B is equal to A. Another one that's pretty obvious that you probably knew about, but you may not have seen it written this way. So if A is equal to B, B is equal to A, it makes total sense. And so I'm going to highlight that as one we should get to know, but it's not too hard to know. It's not unknowable. And here we have the transitive property of equality, which reminds me of one of the principles that we talked about before. I think it's the principle of logical syllogism. We talked about it in the last section. A is equal to B. If A is equal to B, and then I can say B is equal to C, then clearly A must be equal to C. If A is equal to B, right, and B is equal to C, then if A is equal to B, yeah, then A has to equal C. And the transitive property kind of reminds me of like the equality moving around in a way. So I know that I have um, A is equal to B, and so B is equal to C. Well, golly gee willikers, these guys must be equal to each other. This is what I think about in my mind sometimes when I think about the transitive property. I think about kind of this triangular movement here. All right, I hope that this was helpful in you thinking about these terms. Let's go ahead and look at some examples now. So here we are taking a look at this situation. We're going to prove that this, given this, that we're going to end up with this. In a sense, we're solving this equation, and we're going to justify it step by step. So we're going to start off with the given information. So we are given this bit of information, and I'm literally going to put the reason why I can write this down is because it was given to me. All right. The next thing I'm going to do is the first step in solving an equation like this. I'm going to rock the distributive property so I can free this equation or this part of the expression from parentheses. So that would give me a negative 5x plus a negative 5 times 4, and that's equal to 70. And what did I just do? I just performed the distributive property. Distributive. All right. So now that we've got that out of the way, I can simplify this. Negative 5 times x is going to be a negative 5x. And a negative 4 times a positive, a negative 5 times a positive 4, excuse me, is going to lead me to a minus 20 or a negative 20. And how am I able to write this in this way and this in this way? Well, I'm exchanging equivalent statements. And so when I do that, I know that is substitution. That's going to be substitution for me. And the next one I'm going to do is I need to isolate my x term, and to do that I'm going to get rid of everything around x that's bothering it. Right now I'm going to get rid of the minus 20, and I get rid of that by adding 20 to both sides. Okay, and this move that I'm making right now of adding 20 to both sides, I could actually rewrite it like this, where I'm adding 20 to both sides of the equation, and I've highlighted that I'm adding it to both sides to say that what am I using? The additive property of equality, right? The add prop equal sign, right? Add prop equal. So now that I do that, I'm going to join some like terms together, and you guys remember what we did last time. I'm going to replace this with an equivalent statement. So the equivalent statement I have over here is negative 5x, and this is plus 0, or 0 has just gone away. These guys have gone away. And then 70 plus 20 is going to give me 90. And what did I do? I did substitution. Substitution, right? And then the next thing I'm going to do is I need to divide both sides by negative 5 because I want to isolate that, that x value. And what am I doing there? I'm doing the division property of equality. And so what I'll do is I'll actually write this as a separate step. So I'm showing that this step was the substitution, and here is the division property of equality. And you know what I'm going to do next, right? I'm going to replace this. I'm going to substitute this with an equivalent statement. Negative 5 divided by negative 5 is a positive 1, so that's 1x. And 90 divided by negative 5 is a negative 18. And that is the substitution property of equality. All right, substitution property of equality. I shouldn't write sub, I should write substitution. And the reason why I'm going to choose to write substitution here is because when I use sub, I'm going to be talking about subtraction sometimes, like I did add. So that's what we got. And so this, it's not beautiful, but it is an algebraic proof. We did a good job. Let's go on to another example.